Day 91 Notes, Advanced Algebra 2. Today we're looking at how to evaluate particular functions. We have several different ways that we can evaluate a function. Let's first remind ourselves of what function notation is. Function notation is any time that we establish a function with a particular letter. In this case, we're using F, G, and H as three examples. For each of those letters, we're immediately followed by the parentheses surrounding our independent variable, or our input value. In this case, it's an x. So by far and away, the most common way that we list functions is by writing f of x using this notation. But it's not uncommon to see g of x or h of x or other letters partnered with that x there. And we do that. We use different letters at times when several functions are used within the same problem. And again, this notation is reserved for when we're working with a function, not a relation between numbers. It's good for a function, not a relation. That's what this notation is reserved for. We already talked a little bit on Monday how to evaluate functions, so let's go ahead and practice a couple of these. This time I want you to evaluate the functions and write our answer as an ordered pair. You do have to be careful because sometimes our instructions in the future will ask you to do that, to write your result as an ordered pair. So to evaluate this function at -3, we need to establish the result when x is equal to -3. So I'm going to change the letter x to the number -3 and complete the math. 2 times -3 is -6. -6 minus 9 is -15. So f of -3, and it's a good idea to get in the habit of including this description on each line. I forgot to do that here, but I went back and added them now. F of -3 is -15. If I were to write this as an ordered pair, it would look like this: -3, comma, -15. That would be a good solution for this practice problem. If I wanted to evaluate the function g at 5, then I need to think what this function would look like if I change the letter x to the number 5. 5 squared plus 3 times 5 minus 4. Well, that's equal to 25 plus 15 minus 4. 25 plus 15 is 40, and 40 minus 4 is 36. G of 5, therefore, is equal to 36. And as a coordinate, we could say that this is the coordinate pair 5, comma, 36. Using function notation, this is one method that we can use to evaluate functions. While we're on the subject of evaluating functions, I'm actually going to move down towards the bottom of my notes here. And I want to talk about evaluating functions based on a graph. This is a second way that we can evaluate functions. I would like to evaluate f of 0, f of -2, and f of 3 by looking only at the graph, and I'm going to ignore the function or the equation that was written here. F of 0, f of -2, and f of 3 from the graph, and I'm going to write each of these as an ordered pair when I'm finished. Well, to evaluate f of 0, I need to establish what the function value is when x is equal to 0. Now here's my x-axis. It's this horizontal line here. When x is equal to 0, we have to travel down to this point in order to establish my function value. And that value occurs at -2. So f of 0 is -2, and we can write that as a coordinate pair as 0, comma, -2. For f of -2, I need to travel to the left 2 units. And from this spot here, where x is equal to -2, I will travel up to this point, which is +2. Its coordinate now is -2, comma, 2. For f of 3, I need to travel to the right 3 units from the origin, and then look upward to connect with the graph. That brings me to this point. This point occurs at 1, 2, 3, 4, 5, 6, 7 units in the air. When f of 3 is equal to 7, we produce the coordinate 3, 7. We've now just evaluated a function based on a graph. Let's look at another example. This is what we call an absolute value function, and again, I'm going to ignore the equation that's shown here. We're not concerning ourselves with that right now. But I would like to evaluate f of 0, again, f of -2, and f of 3. And we'll establish each of these results as a coordinate pair when we're done. When x is equal to 0, I'm looking at the function 0 units to the left or right from the origin, and I don't have to travel very far to find its function value. F of 0 is equal to 0 at this point. That function crosses the x-axis and the y-axis at the same spot, exactly at the origin of our coordinate grid. That point is labeled 0, 0. For -2, I need to travel 2 units to the left and investigate what the function value would be when I look up from that value of -2 for x. That comes out to be +2. So for this coordinate, we can write -2 in place of x and +2 in place of y. To evaluate at +3, I move 3 units to the right from the origin, and I look upward from here, and I point to this value, which happens to be +3. The coordinate established because of the function value 3 is 3 itself, so we can write 3, 3 as its coordinate. And we've now again evaluated a function based on the graph. Now we're going to take a look back at the second portion of our notes that I skipped over a moment ago. And we're going to take a look at what's called the vertical line test. The graph of a function will pass the vertical line test if a graph does not, let me say that again. The graph of a function will pass the vertical line test. If a graph does not pass the vertical line test, then it's not considered a function. It would be a relation. So this vertical line test is a technique for us to look at a particular graph to determine whether the graph represents a function or not. Each of these examples below are functions, and they would pass the vertical line test. The vertical line test states that if you draw a series of vertical lines drawing them up and down, as we go across the domain of our function, the vertical line test says that any one of these vertical lines will touch the graph at exactly one position, at one spot. Now I've drawn a bunch of those lines in place here. Let's take a look at just a few of those. If I drew the vertical line right here, it only touches the graph at this spot. If I drew a vertical line here, it again touches the graph in only one spot. Each of these vertical lines, no matter where I draw them on this function, will only cross at one spot. Even if I look at the graph below, this vertical line crosses at one spot. This vertical line crosses at one spot. Each of these vertical lines that I draw only cross the graph at one location. Therefore, each of these pictures, each of these graphs, pass the vertical line test. Well, let me give you an example of something that would not pass the vertical line test. Let me start with a quick sketch here. Let's say that I had a relationship drawn that looks something like this. It's possible for me to create a graph so that it comes out looking like this on a coordinate grid. However, if I start drawing vertical lines across the domain, you'll see rather quickly that we run into a problem. Each and every one of these vertical lines actually touches the graph in two locations. So that vertical line had 2 points of intersection. This vertical line has 2 points. This vertical line has 2 points, so on and so forth. Each of these green vertical lines passes through the graph more than once. Therefore, it fails the vertical line test. Fail the VLT. Therefore, the relationship that I used to create this red oval would not pass the vertical line test, and therefore it is not a function. It's simply a relation. Let's try another example. This time, however, I'm going to draw this shape. Let's say we have a graph that almost looks like a cubic graph, but it's turning this way. Does it pass the vertical line test? Well, if I'm looking at this portion of my domain, it would still pass. Each of these vertical lines only touch the graph one time. However, if I move too far to the right, we start to see that it fails the vertical line test at this position, and further as we move to the right. Even if the function fails just at one spot, if there's one vertical line that makes this function fail the vertical line test, then this too would fail the vertical line test, and therefore they are not functions. We're not going to spend any more time discussing the vertical line test in this video, but you might encounter it in your homework tonight, so it would be a good idea to come back and reference it if you need to do so. We're going to shift gears one last time to talk about our final subject for today's notes. And I'm going to ask you to graph the following functions using a table of data. So what we generally do when we use a table of data is we create a list of x and y values and use them to create coordinates that can be plotted on a coordinate grid. Now for us, the x value is what we would call our independent variable. It's the x value that we're allowed to choose what to investigate. Now, for me, what I like to do is I like to pick numbers usually somewhere around the origin. So I'm going to pick a pair of numbers to the left, the origin value itself, and a pair of numbers to the right. And that's going to give me a pretty good idea of what this graph might look like. Now, to find out what our y result will be, I need to evaluate the function at each of these x values. So off to the side, I'm going to complete the math for f of -2, for f of -1, for f of 0, f of 1, and f of 2. Now at -2, I'm looking at the number 2 times -2 plus 9. And 2 times -2 is -4. -4 plus 9 is 5. 2 times -1 plus 9. Whoops. I have to be careful here. I have to look at my math again. This was actually supposed to be a -9. So let's correct that. -4 minus 9 is equal to -13. 2 times -1 minus 9. Well, that's -2 minus 9. That's -11. At 0, 2 times 0 minus 9 is -9. And at 2 times 1 minus 9, that's 2 minus 9, which is -7. And 2 times 2 minus 9 is 4 minus 9, which is -5. To sketch this graph, we'll start with a coordinate grid. And I'm going to fill in the rest of my table before I move too far. At -2, we had -13, -11, -9, -7, and -5. You may have noticed the pattern that developed here. which is perfectly fine to work with because this is what we call a linear function. The numbers will change by the same amount each time. Let's go ahead and create the coordinates associated with each of these points. At x equals -2, my y value is -13. So I'm going to go left 2 units and down 13 units. Now my scale has to be modified a little bit. I'm going to call this -6 and this -12. We'll call this one +6 and we'll call this one +12. So if I go left 2 units and down 13 units, that would put me at a dot right about here. For my other coordinate, I can go with -1, -11. So I'll go left 1 unit and down 11 units. For my next coordinate, I can go over 0 units and down 9 units. That's right in the middle between 6 and 12. I can move to the right 1 unit and down 6 units. I'm sorry, down 7 units. And then lastly, I can plot this point right 2 units from the origin and down 5 units. I have a series of points now that can be connected with a line, and in this case it's a perfectly straight line, and that line would represent our function. In the interest of time, since I recognize that this video is starting to run a little bit long, I'm actually going to stop here. I would encourage you to try graphing these other 2 examples on your own, and come to me with questions tomorrow if you find that you're not successful in graphing them. Or I will post these on the overhead tomorrow so that you can compare your graphs with mine. Thank you, good luck, and let me know if you have any questions.